Welcome to a deep dive into the revolutionary structural mechanics of the AEON-CASIMIR propulsion system. In this chapter, we challenge a core misconception in advanced propulsion that a craft undergoing extreme acceleration or space-time curvature must inevitably transmit those forces to its structure and occupants. Instead, the AEON-CASIMIR architecture reimagines the hull not as a load-bearing frame, but as a sophisticated interface between engineered fields and locally flat spacetime. This approach fundamentally changes how we think about structural integrity and occupant safety in high-performance vehicles. One of the key innovations of the AEON-CASIMIR system is the offloading of structural loads into engineered fields. Rather than allowing inertial forces to pass through the hull, these forces are geometrically canceled by the surrounding fields. The hull exists within a protected metric pocket, ensuring that occupants experience near-zero inertial stress, even during maneuvers that would be catastrophic in conventional vehicles. This field-mediated approach represents a paradigm shift in how we design for extreme environments. In traditional Newtonian flight, the equation F equals ma dictates that acceleration results in force transmission through the structure. This means that every maneuver, every burst of speed, puts stress on the hull and its occupants. However, in AEON-CASIMIR flight, local acceleration is nearly zero. Motion is achieved not by pushing against the structure, but by translating the metric of spacetime itself. If the structure were allowed to couple directly to curvature gradients, the craft would be torn apart by the resulting forces. The AEON-CASIMIR hull is not rigidly embedded in the propulsion field. Instead, it is suspended within a field-mediated inertial null zone. Inside the crew volume, the metric remains locally flat, preserving normal conditions for occupants. Outside the hull, the engineered metric can be dramatically different, tailored for propulsion. The hull thus acts as a boundary between two distinct space-time metrics, ensuring that internal stresses are minimized and the structure remains intact. To achieve this remarkable decoupling, the AEON-CASIMIR system employs a multi-layered field hull coupling strategy. Each layer serves a specific function, from isolating the hull from curvature gradients to absorbing transient impulses. This layered approach ensures that the hull only ever experiences residual stresses, never the full brunt of acceleration or environmental forces. Let's explore each layer in detail to understand how they work together to protect both the structure and its occupants. The first layer is the metric isolation envelope. This layer is responsible for canceling curvature gradients across the hull's thickness. By ensuring that the difference in the engineered metric across the hull approaches zero, the system prevents destructive stresses from developing. This isolation is crucial for maintaining the integrity of both the hull and the internal environment, regardless of the external spacetime conditions. The second layer is the electromagnetic stress buffer. This layer absorbs shear forces through controlled Lorentz forces, acting as a dynamic shield against sudden changes in stress. The maximum stress it can handle is determined by the strength of the magnetic field and the permeability of the medium. This buffer ensures that any residual forces are dissipated before they can impact the structural hull. The third layer consists of plasma shear dampers. These dampers use plasma flow to absorb transient impulses, acting as a cushion against sudden shocks. The damping coefficient depends on plasma density and temperature, allowing for real-time adjustment to changing conditions. This layer is essential for smoothing out any remaining disturbances that pass through the electromagnetic buffer. Finally, the structural hull itself forms the last layer. Unlike traditional designs, this hull is not responsible for bearing thrust or G-forces. Instead, it only resists residual stresses and environmental loads that have already been mitigated by the previous layers. This allows the hull to be much thinner and lighter than conventional designs, focusing on field transparency and precision rather than brute strength. Because the hull does not experience thrust loads, G-forces, or thermal shock, it can be constructed much thinner than traditional aerospace structures. The primary requirements for the hull are field transparency, electromagnetic compatibility, and vacuum boundary precision. Materials are chosen for their behavior in engineered fields, not for their ability to withstand massive mechanical forces. This opens up new possibilities for lightweight, efficient designs. In the AEON-CASIMIR system, materials are selected based on their field behavior rather than their mechanical strength. The hull must be transparent to engineered fields, compatible with electromagnetic environments, and capable of maintaining a precise vacuum boundary. This focus on functional properties rather than brute strength allows for the use of advanced composites and novel materials tailored to the unique demands of field hull coupling. A key benefit of this architecture is the inertial isolation of occupants. The crew is enclosed within a local inertial reference frame, meaning that even during instant vector changes, right angle turns, or apparent hypersonic maneuvers, no inertial stress is transmitted to them. This is achieved by maintaining geodesic deviation near zero within the protected metric pocket, ensuring a smooth and safe ride regardless of external conditions. Geodesic deviation measures how nearby paths in spacetime diverge or converge. In the AEON-CASIMIR system, the deviation is kept near zero for occupants, meaning their paths remain parallel, even as the craft undergoes extreme maneuvers. This is a direct result of the metric engineering that isolates the crew from external spacetime curvature, ensuring comfort and safety at all times. Traditional vehicles subject occupants to intense forces during rapid maneuvers. In contrast, the AEON-CASIMIR system allows for instant vector changes and right angle turns without transmitting any inertial stress to the crew. This is possible because the local metric inside the hull remains flat, decoupled from the engineered metric outside. Occupants feel as if they are stationary, even as the craft performs extraordinary feats. Structural resonance can be catastrophic in conventional vehicles, leading to destructive vibrations. The AEON-CASIMIR system avoids this by detuning the coupling between the fields and the structure. The natural frequency of the hull is kept distinct from the frequencies of field oscillations, and plasma buffers further damp any residual coupling. This ensures that resonance is never a threat to the craft's integrity. The natural frequency of the hull, determined by its stiffness and mass, is deliberately kept different from the oscillation frequencies of the engineered fields. This prevents resonance from developing, as there is no overlap between the driving frequencies and the structure's response. Plasma buffers add an extra layer of damping, absorbing any energy that might otherwise build up in the hull. Rather than specifying exact compositions, the AEON-CASIMIR system defines hull materials by their functional behavior. Key requirements include low magnetic permeability, controlled dielectric response, high dimensional stability, vacuum boundary precision, and resistance to Casimir pressure gradients. These materials are advanced composites, optimized for compatibility with engineered fields rather than for armor-like strength. Low magnetic permeability is essential for minimizing unwanted interactions with the engineered fields. Materials with this property ensure that the hull does not distort or absorb magnetic flux, preserving the integrity of the field-hull interface. This is a key factor in maintaining the effectiveness of the metric isolation envelope and the electromagnetic stress buffer. A controlled dielectric response allows the hull to interact predictably with electromagnetic fields. This property is crucial for the electromagnetic stress buffer, ensuring that the hull can absorb and dissipate energy without developing hotspots or weak points. Advanced composites are engineered to provide this precise response, contributing to the overall stability of the craft. High dimensional stability ensures that the hull maintains its shape and precision under all conditions. This is vital for preserving the vacuum boundary and for ensuring that the field-hull interface remains consistent. Materials are selected and engineered to resist deformation, even under varying thermal and electromagnetic loads. Maintaining a precise vacuum boundary is essential for the operation of the AEON-CASIMIR system. The hull must prevent any leakage or deformation that could compromise the internal environment. This requirement drives the selection of materials and the design of joints and seals, ensuring long-term reliability and performance. The hull must also resist pressure gradients arising from the Casimir effect, a quantum phenomenon that can exert significant forces on closely spaced surfaces. Advanced composites are engineered to withstand these gradients without deforming, ensuring that the hull remains stable and the internal environment is preserved. If the field isolation degrades, curvature gradients across the hull begin to rise. In response, the electromagnetic buffers activate, and plasma shear increases to absorb the additional stresses. If these limits are exceeded, the metric envelope downscales, and the craft transitions to an inertial-normal mode. Even in these scenarios, the hull is never subjected to destructive loads, thanks to the layered protection system. When the protection layers are overwhelmed, the system transitions to an inertial-normal mode. In this state, the hull and occupants experience forces similar to those in conventional vehicles. However, this is a last resort scenario, and the design ensures that the hull can still withstand these temporary loads without catastrophic failure. The core design principle of the AEON-CASIMIR system is that the hull does not resist motion through strength, but is instead carried by geometry. Structural integrity is maintained by decoupling the hull from external forces, allowing it to float within a protective field envelope. This approach redefines what it means to build for extreme environments. To recap, the AEON-CASIMIR hull is protected by a series of engineered layers: the metric isolation envelope, electromagnetic stress buffer, plasma shear dampers, and the structural hull itself. Each layer plays a critical role in ensuring that neither the structure nor the occupants ever experience destructive forces, even during the most extreme maneuvers. Metric engineering is at the heart of the AEON-CASIMIR system. By precisely controlling the space-time metric inside and outside the hull, the system creates a safe, inertial environment for occupants, while enabling extraordinary maneuverability. This practice requires advanced computational models and real-time field adjustments to maintain stability under all conditions. Let's visualize the field hull coupling in the AEON-CASIMIR system. The hull is suspended between two distinct space-time metrics, with each protection layer clearly defined. The metric isolation envelope surrounds the hull, followed by the electromagnetic stress buffer and plasma shear dampers. Inside, the crew enjoys a locally flat metric, shielded from all external forces. This schematic illustrates how inertial isolation is achieved for the occupants. The crew volume is depicted as a region of locally flat spacetime, surrounded by protective field layers. Geodesic deviation is minimized, and no inertial stress is transmitted, even during rapid maneuvers. The diagram highlights the separation between the internal and external metrics. This schematic demonstrates how structural resonance is avoided in the AEON-CASIMIR system. The hull's natural frequency is shown as distinct from the field oscillation frequencies, with plasma buffers absorbing any residual energy. The diagram emphasizes the deliberate detuning of field structure coupling. This schematic outlines the system's response to a failure in field isolation. As curvature gradients rise, the electromagnetic buffer and plasma shear layers activate to absorb the increased stress. If limits are exceeded, the metric envelope downscales and the craft transitions to inertial-normal mode. The hull remains protected from destructive loads throughout the process. This schematic categorizes the functional classes of hull materials used in the AEON-CASIMIR system. Each class is represented by a block, with properties such as low magnetic permeability, controlled dielectric response, and high dimensional stability listed. The diagram emphasizes the focus on field compatibility over mechanical strength. This schematic illustrates the stress pathways in the AEON-CASIMIR hull. Arrows indicate how external forces are redirected and absorbed by each protection layer, preventing transmission to the structural hull. The diagram highlights the effectiveness of the layered defense system. This schematic focuses on the concept of the metric pocket. The crew volume is shown as a region of locally flat spacetime, completely enclosed by engineered field layers. The diagram emphasizes the separation between the internal and external metrics, ensuring occupant safety. This schematic demonstrates the importance of field transparency in hull materials. The diagram shows engineered fields passing through the hull with minimal distortion, highlighting the need for materials with specific electromagnetic and structural properties. This schematic details the operation of the electromagnetic stress buffer. The diagram shows magnetic field lines interacting with the buffer layer, which absorbs and dissipates shear forces before they reach the structural hull. This schematic illustrates how plasma shear dampers function. The diagram shows plasma flow within the damper layer, absorbing transient impulses and smoothing out shocks before they reach the hull. This schematic shows the hull operating in inertial-normal mode, the fallback state if all protective layers are overwhelmed. The diagram depicts the hull and occupants experiencing conventional forces, but the structure remains intact due to its engineered resilience. This schematic emphasizes the principle that the hull's integrity is maintained by geometry rather than strength. The diagram shows the hull floating within a geometric field envelope decoupled from external forces. This schematic represents the experience of occupants inside the AEON-CASIMIR craft. The crew is shown in a calm, undisturbed environment with all external forces neutralized by the surrounding field layers. This schematic details the interface between the hull and the engineered fields. The diagram shows how the hull acts as a boundary condition, with field lines bending smoothly around it and no direct force transmission. This schematic shows how the hull resists only environmental loads, such as micrometeoroid impacts or radiation, while all acceleration and inertial forces are handled by the field layers. This schematic presents the sequence of field layers from the crew volume outward. Each layer is labeled and its function briefly described, providing a clear overview of the protection strategy. This schematic highlights the use of advanced composites in the hull. The diagram shows the composite structure at the microscopic level, with fibers and matrix materials arranged for optimal field compatibility. In summary, the AEON-CASIMIR system represents a radical departure from traditional structural mechanics. By decoupling the hull from external forces and relying on engineered fields for protection, it achieves unprecedented levels of safety, efficiency, and performance. This approach paves the way for future vehicles that can operate in extreme environments without compromising structural integrity or occupant comfort.